And we're live, folks. Welcome, everybody. Thanks for being here. Today, we're going to be talking about end-fed half-wave antennas, specifically little teeny tiny ones for low-power operation. Joined with a couple of buddies of mine, Chuck, KK6USY Ham Radio Adventures. Below him is our buddy Ziggy, the 75-ohm ham, who is a creative antenna builder in his own right. And then off-screen, we've got the Professor Emeritus, I think is how you say that, Mr. Hollywood. How you doing?
Hiding in the pine bush.
Well, I'll take your word for it. I don't see the pine bush, but I believe you're in it.
Oh man, that's great.
Anyhow, thanks. Yeah, thanks for being here, everybody. Appreciate it. Hey, Doc Brad, how you doing? So we were chatting last night, Ziggy and I. Was it last night? Might have been the night before. And he's like, "Hey, let's do a live stream." And
was it me? That was you.
Was it me?
Yeah.
And then so we decided to live stream, and we're talking a little bit about these little tiny antennas that Chuck pinged me like 2 weeks ago. Here's one right here. We'll get a better look at it in a little bit. And he said, "Hey, I'm working on this little teeny tiny antenna. You want to play along?" And of course. So Ziggy, yours is in the mail, or did you get it yet? The frame?
Oh, that thing is on its way. It'll be here any minute.
So maybe we'll get it on air live.
Well, it happened to be 4th of July weekend, and I didn't realize that I could have sent it on Saturday. By the time I realized it, I only have till noon, so I was too late.
I went and overnighted a Coroid so I could wrap up for it and everything. I'm sitting here in anticipation.
I got my toroids today.
Yeah,
there's my nothing's wrapped yet.
Oh, yeah, there you go. What did you print that out of, Chuck?
I run PETG for everything, pretty much.
So I did ASA, and I mark everything, so you can see the ASA on there, so that way I know. But a couple of the original prototypes that you sent over, like I typically will do something. You're never going to show up because the green screen. I'll have to go in overhead cam. But let me do that real quick. I print stuff in PLA first. There you go. You should be able to see my messy desk. And let's do this and this, and that's not going to do it. Let's do that. Let's do that. There we go.
I should have.
And so here's the first one. I printed it in PLA, but if you notice, it doesn't have any holes in this part of the frame for the ground lug. So I called Chuck and I said, "Chuck, hey, you got to put ground holes in this thing." So he sent the new STL over, and I printed this one out. That's got the holes in it for the ground lug. And here's how I set that ground lug up. You know, I got one of the ones, Chuck, that you did like this with the SO239.
Yeah, I was looking for that one, but that one's on the way to Ziggy.
Yeah, what I'm worried about is that once you put a coaxial piece on here, it might not fit because of the lug. You know what I'm saying?
I think it'll fit. Don't you have a coax cable to put on there?
But see, if you take a look at this one, it fits with the NC connector on there.
Yeah, I can always change that too. That's no big deal.
Let's get the comments real quick. Bass Angler, thank you, bro. We give a $5 super chat. Much appreciated.
That's awesome.
And look at this. We've awakened. And then our buddy Shane from Adventures in Blind Videography. How do you know when to attach the little antenna directly to the radio, and when do you have to attach the antenna via coax? I'm going to ask Hollywood to help me out with this one, but I would never attach an antenna directly to a radio for HF, especially something that is unbalanced, like an off-center fed dipole or well, let me take that back, like an end-fed half-wave or random wire antenna. Because you don't.
If you watch Peter Parker, BK3YE, he generally does connect directly to a tuner that's right on the radio. There's no coax at all.
Yeah, I've seen where people have done it, but you're feeding your shield side right into your radio, right? Common mode current right in your radio, and effectively, aren't you kind of making your radio part of the antenna system at that point?
You are, and you also are with coax.
Very
Yeah.
true. And also my Daiwa tuner, it came from the factory with a terminal, a single banana plug output. I mean, they expect you to just raw hook up a wire to the back of this thing. Tio and I did this at Hamcation in Orlando. We just had some random piece of wire up and over my truck and just some random scrap wire, and we walked all over all the bands, and we had a great time.
Well, hooking it directly to your tuner is not the same as hooking it directly to your radio, though, right?
Oh,
You still
no,
have
Yeah,
the ability to choke.
Correct.
choke
Yeah,
the
you
counter.
truck it something different there.
But if the vertical is a quarter wave resonant, it's 36 ohms J0, so you can connect it directly in, no problem.
You better be spot on with your length.
And an SO239, remember, kids, will accept a banana plug.
That's right. You can get creative with it.
Everybody forgets that, right?
Yep.
Yeah.
But I wouldn't hook it directly to the radio. That's just me. I would put a little bit of separation in there, and I would put it.
Well, you
put a
are
choke-
cautious ape. That's
I
your
am,
nickname,
right.
cautious ape.
That's right, Dave. They changed the layout in StreamYard a little bit. I noticed that.
Yeah.
I'm sitting here
There was
all.
When
all
I came in, and
confused.
I didn't have time to read it.
William saying his club's building a QRP Z match manual tuner in August. That's awesome. I wish my club, but I don't belong to, would do something like that. I might have to belong to them.
Yeah, you might have to join up.
Yeah, it'd be pretty fun.
Maybe you could head that off.
But I guess I'll talk a little bit about some of the construction details that we had on here. And, we're still trying to figure out what we're going to do with these things and like what the final recommended build's going to be. But we wanted to have a NFED that was 20 watts capable, and that's 20 watts single sideband or digital, right? So you could do either one. So that way you could use it with a G90 or any of the QRP radios that are out on the market. Does that sound about fair or right?
Yeah, there's a couple radios out now that will do 20, like QRP type radios that do 20. I forget that
FX4
FX4. Yeah, that one. Yeah, that one's that way also.
That's a 20 watt or two, right? What other ones are 20 watts? I'm drawing a blank.
Well, the KX3 is 15 watts with the external battery, I think. And my KX2 does 12 watts, but it's not easy.
My
to
705
do
10 with the external battery. But let me show you some.
We like to have a little headroom too. I mean, there's a lot of companies throwing out the ones with like looks like 50s and saying, "Oh yeah, you can do 20 watts with it." And I'm not sure if they're stacking two of them or what, but I mean, I think I did one once, and I think I could do like 30 watts out sideband with a double 50, but those are hard to wind. They're tiny.
I tell you, the one that I did, this one here, this is an FT82. This is a 114.
Mm-hmm.
Wrapping the 114 really wasn't a problem, even though I did the 3 to 21 windings. Going to 3 to 21 on the 82, that was a little tougher. But I used a thinner gauge wire. But here's a couple different cores that we were kind of messing with. This is the FT50. They're all mixed 43. This is the 50. That's a half inch across, and that this thing, it's just too dang on small, and you can't really get enough. You can't get much power out of it. One, there's no way it's doing 20 watts. No way it's doing 10. You might be able to get 5 SSB, but if you're pushing 5 watts single FT8 through that, you're going to have problems. Then we looked at these FT82, so it's 0.82 of an inch across 43s, and that's the one we wound on here. But we kind of like this one. This is the 114, and actually this is mix 61. And here's what's kind of crazy. I got these mix 61s, but if you look at them right there, it's about the same color. They're a little bit chalkier and a little bit lighter than the 43s.
They're a real pretty gunmetal gray.
Well, he sent me. I ordered 43s and 61s. Yeah. But the 43s, I'm thinking he might have accidentally reached in the bag and grabbed the wrong ones.
You can usually tell the difference in between 43s.
These are exactly the same.
Uh-oh.
So I did a video where you take a piece of wire and you wrap it around here like 10 times, and then you feed a signal through it, and then you look at the frequency response across the wide sweep, like from I don't know, 3.5 megahertz to 30 megahertz, and it will be different for different cores. And so it's just a pain in the ass. So, but that I'm just going to go ahead and test them and see what happens. Some cores you can hit with a multimeter, and you can read conductivity through it, like a resistance measurement. But I don't think that's I think that both of these you would just show an open load.
Oh, no.
I'd like to hit mine with a heat gun and see where they lose their inductance.
Yeah, I'll be right back. Okay. I'll be right back.
All right, like once they're wound up, you can heat the core up to a certain temp. Is that what you're saying?
Yep, stick it in the oven.
So if you'll embiggen me for a minute, let's catch everybody up as to what we're talking about, so that we're all on the same page.
There we go.
Everybody see it?
We see it.
Okay, it's a little fuzzy. It's not your eyeballs, guys. Don't worry. So what we've got our feed line, and it's coming in, and this capacitor we'll talk about later, but we're going to hit a transformer. The transformer is going to have so many turns on the primary and so many turns on the secondary, and this one even shows you that it's a tapped, my favorite winding style. And at the end of our secondary, we're going to have a high impedance output to our long wire in-fed antenna. And the go-to that everybody has burned into their brain is the 43 mix with a 214. Do some division. It's a 7-to-1 turns ratio. And that gets you in the neighborhood of what the books say, somewhere in between 1,000 to 5,000. Now, here's the thing: the higher the impedance, the harder RF has a time with, and anything over 5,000, I read, is like really pushing the upper limits of trying to shove some RF down. Some you're talking
about impedance on the primary,
on the output of the secondary. Well, I mean the impedance of the entire transformer, basically. What did I miss, Hollywood?
No, you're right. You're absolutely correct. You're absolutely correct. In fact, I'll go one step further. At WBZ in Boston, just bear with me. Those are end-fed half-wave vertical radiators. There's 2 of them, okay? They are not exactly 180 degrees. Why? Because exactly what Ziggy said. It's very high impedance when it's exactly a half-wave long. And it's a tough sell to get it to accept power. So what they do is they go 10 degrees further. It's 190 degrees. And now it'll take power.
When you say 190 degrees, though, you're talking about a delay. So
no, the electrical degree, the length of the radiator. A half wave is 180 degrees. It's a half of a circle.
Right.
So they go 190 degrees. So it's slightly capacitive. If you go from a quarter wave to a half wave, the longer you get it towards a half wave, it has more and more inductance. And then when you get to the half wave point, it flips. It's like balancing a pencil on the tip of your finger. It's very unstable.
You cross the hemisplat in the Smith chart, right?
Yeah. The SWR Rubicon, right?
The hemisplat.
Let me do.
So on the other side of the half wave, it becomes capacitive.
Yeah. So what I was under the impression of is that when you take an end-fed half wave, so here's the core, and if I just hook this up to ground and this one up to the center conductor and feed this into some coax into my nano VNA, what I want to look at is the open inductance across the primary. And what they say is that should be around 4 times the characteristic impedance of whatever your transmission line and system impedance is, right? So you would want to see an inductive, right, reactance of around 200 ohms or greater on the lowest band that you want to operate on. And that tells you if your core has the magnetic flux capability to be able to support the antenna.
Right.
To get down to that low frequency that you're after.
Yeah, well, the lowest one that you intend to operate on. And that's where it becomes a little bit challenging.
We're going to fix the higher ones later.
Here's a 61 core.
I love how he labels every single one. He called me. I got some cores in the mail. He called me and he goes, "Did you label them?"
His penmanship is perfect. It's like the werewolves of London. His hair was perfect. Well, look at the penmanship.
Well, this is a mix 19.
Ape.
I thought it was a 61, right?
Ape writes with his left hand just for a challenge.
Right. But so what we did with these smaller cores is, so when a core, we got a Chuck, there it is. When you have a core and you put a winding on it, you get a certain amount of inductance per wrap or per winding, right?
Yep.
And when you have a bigger core like this one's a 140, you need less wraps to get that level of inductance that you want. When you go down to the smaller core, you have less cross section in the core, so it generates less magnetic flux. So we went with the 321, so we get more winding on the primary. We get 3 of them on there. The challenge is that when you have all of these wraps next to each other like this, they generate capacitance because you have
Right.
2 conductors next to each other.
That's right.
And I'm a big dummy because I didn't measure the open inductance on the primary on these until after I put the parallel resistors in place, right?
And
sorry,
that's also why you're putting a cap on the primary.
Yeah.
I'm calling it the primary, the short turns, because it's equal. You're actually creating a pi network.
Yeah, like a tank circuit, right?
It is a tank circuit, but it's on either sides. You've got inductance and capacitance because each time a winding wraps around itself, there is capacitance between each wire, each wrap.
Right.
So that's total capacitance and inductance. And then on the short side, the 3-turn side, you've got inductance without the capacitance, and that's why you're adding that blue capacitor there.
Well, the other thing is that, so when you have all this inductance, because you want it to be at a certain level and the lowest frequencies you're going to operate, the inductance goes higher as you go up in frequency, right? So
the reactance goes higher.
Yes.
Yeah. So putting this cap on there helps smooth out your SWR. But now because the cap's on here, I can't measure my open primary inductance, because when I measure it now, I'm measuring the pi network, right? I'm not measuring the primary. So,
and let me step in on that. So when I first got into infed half waves, the beautiful thing is that I wasn't taught by anybody. I didn't know anything, and I have all these hundreds of hours of field time and like can't do it, actual time out there in the field, playing with number of wraps and coils and stuff like this. And what I noticed is that you can't have it all. You can't have an 80 through 10. The reason why that they put the cap in there is to fix the higher bands, because you've technically made a transformer that works really good on its lowest fundamental frequency. But as you notice, I call it the stairway to SWRs. It kind of goes
you got to do some kind of adjustment.
So once you put that, you're basically putting the tuner out there with the cap. Correct. And it's going to calm down, but it's not going to fix the antenna. But it's going to give you and your radio the ability to pump RF out. So my new thing when I've come full circle on these things is that, what are we making here? Are we trying to conquer the high bands, or are we trying to get a long wire? Because you're going to need a lot less wraps for like something that's going to do 80 and 40 meters. You want to do the higher bands, you actually need more impedance presented to your antenna. You're going to need more wraps, and you're going to need a core specific to that, specifically mix 61. That was a lot.
So this is why we have the 61s, and we'll probably end up going with the 61 on these antennas, because they're designed for 40 or their purpose is 40 to 10, right? Because they're lightweight and all that kind of stuff. So if you were going to go lower than that, 43 is probably more appropriate. But when you're looking at higher, I think you do get a little bit better performance out of a 61 core.
What'd you do? Glue that?
I did. I dropped it on my tile.
Oh, dear.
And I want to tell everybody it's okay, because technically, magnetically, it doesn't know that you broke it.
Well, it's like a snap-on bead, right?
That's
like a snap-on,
like a snap-on bead. I couldn't find this little chunk. It's in my kitchen somewhere, but I gave it a day to dry. And I wrapped it. And Ape and I were talking about, coupling and tapping and the intercapacitance winding. And then I stumbled across what this is called. This is called a hybrid winding for the infed half wave. Mm-hmm. If you ask me, guys, just let you know, I don't do a crossover winding. Some people like it. I don't do it. So this is what you're looking at.
Thanks,
one contiguous, but see right around like 8 to 10 turns here. See how I start respecting the intercapacitance winding? So
Right.
I get this tight coupling at the beginning, but for my higher bands, I'm doing myself a favor here. So this isn't matched yet, and Chuck pointed out that I've got one too many wraps, but anybody that knows me, this is how I start. I put too many wraps on it, and this way I can take off a wrap, hang it, look at it.
Yep.
Hang it,
You're,
look at
you're
it. Hang it.
reducing the capacitance between the windings. You're also increasing the voltage breakdown between windings, because that's where the HV is.
Oh yeah,
the
it
end.
starts getting
Well-
real nasty.
Well,
towards the
what's
end.
interesting is that so you have a, I don't know what that is because you have extra wrap on there, but like if you did the 321,
This would be a 49 with extra wraps.
right?
But it's gonna be less than that because I'm targeting 40, like 6 to 40.
Well, the thing that I was going to say is that you have the turns ratio in an ideal, like, so when you figure out that turns ratio, that is if the core was ideal, but you actually have leakage, induction leakage there, and then you also have parasitic leakage as well, parasitic induction leakage, and your effective turns ratio is different than your actual physical turns ratio.
Oh yeah,
So
and that changes by core type.
Yeah, well, you measure it by taking a look at the actual input versus output. So you'd have to measure the primary with the secondary shorted, and then measure the secondary with the primary and shorted, and then do a ratio of the inductance, and that will tell you what your effective turns ratio is, right? And it can vary with the core type, the wire type, and all that other crap.
It's an auto transformer, and I think a good way to look at it is the
said it.
difference. Where is it resonant? But on the primer from the ground connection all the way out to the end. Okay,
What's up, Andy?
and where you tap it is the ratio of what the coax, what the input is going to see. You can tap it at any point. It just so happens that we've decided that it's a 7 to 7 to
1.
Yeah, 7 to 1 ratio. It gives you 49 to 1.
Well, the other thing I want to talk about Hollywood, and I'm glad because you're kind of reminded me of it, is that if let me go like this real quick. If I take a look at this one, so this one is the auto transformer, or the tapped is what people call that in slang. I don't know if you can see it there.
Mhm.
And then this one has got the twisted primary.
Sold it?
And so
Load it. Yeah, I sold it.
You-
I need you to help me load it.
I'll be back. I'll be back.
All right. So we twist these wires together to have them couple, right? So you get your coupling between your primary and secondary, and then you have your magnetic transfer.
Yeah, I'm not sure I agree with that. You can tap. It doesn't matter whether you tap it or you wrap a double winding. The whole theory behind doing the double winding is not so much that they couple. It's that it's double the thickness of the wire, so it's able to handle more amps because it's a lower resistance value.
And so what I was seeing is that they say that your induction leakage is actually less with the auto transformer because they share the same wire. You still have leakage, but then the twisting them together like this, assuming that they're not shorted together.
Oh, so the
You
one towards your fingers it's wrapped on top of the main coil?
No,
they're
one's tapped
twisted.
and one's twisted.
So the big ones like this, where we have the primary
Right.
twisted. This one is the auto transformer, where it's a single tapped wire. I don't know if I can get that.
Right. Electrically, as far as I'm concerned, they're both the same.
Electrically, they're both the same. However, I tend to disagree a little bit because you now have introduced all this gappage and distance away from the core as you try to make a twist of wire try to stay on top of the surface we're trying to couple to. It just doesn't make sense, but it makes for assembly real easy.
Yep.
Yeah.
But so for this one, the magnetic field that's generated in the primary is supposed to couple with the secondary, despite that they even have the shared ground. But when you share the wire like you do in the auto transformer like this one, theoretically that you have less leakage between the primary and secondary of just inductance bleeding out, the magnetic field bleeding out everywhere.
Also, there's two things going on.
But
now.
you also don't have isolation in the core between your antenna and your coax, right?
No, as long as you bond that transformer to shield anywhere, the entire
Right.
that's all out the window.
Right.
And you actually have one that you made a while ago. That one, yeah. And this is we've been fantasizing about having a totally galvanically
Yep.
isolated
I've seen this model. Yep.
scenario. However, in my test, it's terrible.
Yep.
It looks beautiful. The theory's fun to dream about.
Well, the thing that bothers me about it is that you don't have like static bleed off right from your antenna because it's not grounded. So you have all that static charge that builds up on your antenna.
That's okay. It can stay out there.
And then this one's got the silver mica capacitor. Originally, this big one had this silver mica capacitor on there because I couldn't find my ceramics. I think the silver micas might actually technically be a little bit better, but
They are. They are. The little blue ones are not so good.
Well, these are the RF TKDs.
Yeah, but I know, but no. Silver mica for the
Silver
win.
mica.
Yep.
For the win.
But that's what I have on this. This is a 140 core. Now this one's got 3 wraps on the primary, and then it has, I guess it's 18 on the secondary. So this would be a 36-1.
Mm-hmm.
A low
And
hander.
I put this thing together, and I actually don't recall ever hooking it up and using it. So
That's when we were talking about trying to do this, and you pumped that one out. We never got a chance. It's real hard for Ape to test some antennas living in the real nice neighborhood that he does.
Right. Everybody gets all uppity with me.
Well, nobody even told me about that one. I don't think.
I did a video on it. I think.
Oh no! Here, I want to share this real quick. This is the stairway to swerves, as I call it, and this is typically what you'll expect if you build an infed and it's almost perfect, right? But I did this real quick just so that I could show everybody. This is your standard no capacitor infed, and see how we walk up per the band. Now, impedance-wise, it's matched best for 80.
Right.
And as we put another fold and another fold and another fold on this wire, it gets harder and harder and harder because technically we didn't make this antenna for 10 meters. We made it for 80 meters. If I had added more wraps to it, I've shown this before where you can actually make this whole thing roll forward, and you can add more impedance transformation, and you can actually make it a high bander antenna, but a long wire. Now, the sacrifice is that over here 80 and 40 and everything below is going to start rising, but that's okay because we're all grown ups. We understand that one antenna is not going to provide us a perfect match from
Are you
DC to
saying it's a
daylight.
compromise?
It's a complete compromise, Hollywood. You're absolutely on
exactly.
the nose there.
Exactly.
Yeah. So
you can't always get what you want, but sometimes you get what you need.
That's right. 28 megahertz.
Zach is he's agreeing with Hollywood here. He says a common misconception that tap is just a construction technique. Hollywood is correct. They are the same electrically. I've seen some tests.
Checks in the mail.
Where people put them back to back and do an efficiency test, and they show the auto transformer generally is.
It's got a couple of decimals better. Yeah.
I don't think it's enough for anybody to notice. And one of the things I thought that the auto transformer was a real pain in the ass. However, when you twist them as opposed to tapping them, it's actually pretty easy build. I was surprised.
The twist is my new favorite. The twist tap method. I wanted to share this because this is an infed I did real quick as you guys were talking. I can't believe I was able to crank this out. But there's the counterpoise conversation. I don't know if you want to get into that just yet, Ape.
Well, I always counterpoise. That's just what I do. Because I think it helps with RFI, but I also think it's the other half of your antenna to give you something to kind of work against. The other thing is I don't want any currents on my coaxial. The reason I don't want any currents on my coaxial is one is it kind of can turn that into a radiator where it projects, right, where it radiates energy and will mess up your far field plots because it's part of your antenna at that point going off. You have to be real careful about how you route your cable.
And my my WSJT keeps closing.
the other thing is that when you use your coaxial cable, if your station's grounded, you're routing all of that energy to the low to the ground, right? Because it's looking for the lowest impedance path to ground. When you use a counterpoise kind of acts like a capacitor where it stores and releases energy. That doesn't happen on your coaxial cable. My personal opinion is I just think it's a terrible idea to use your coax that way. But
a lot of people, don't have counterpoises on their end feds, but again, they're portable and they've got, some length of coax, and they're not, earth to ground. They're not ground to earth at the moment, and it's fine. It's totally fine. No harm, no foul. It's all one big antenna system at that moment.
yeah,
But,
so I mean, using the coax to me just seems like it's it's something you can do, not something you should do.
Absolutely. Now, let's see where to start with this. The currents on Hollywood, you're gonna love this. I learned how to say this in a very smart way recently. The
This ought to be good.
reason, yeah, this is gonna be great. The reason why we have a like a, what was it, ape? Like, is it 5 or 10? It's 10%, right? For the counterpoise, is that what we've
Yeah,
been going by?
5% of the antenna length is, but you have to dick with it because of
Well, so
velocity.
I figured out why just the other day. I read it in an old article. You want to give your stray current a low impedance path.
Yeah, and
Yeah.
as a
Right.
so that's the point, right?
As opposed to a high. Yeah, you want to give it a low impedance path, something that it wants to run into. It wants to go into here and just have a grand old time. And so here's the thing, right? To achieve this, technically, this counter tail is going to be some fractional metric of a non-resonant piece of wire to your fundamental to achieve that. And so I got a little nerdy laugh out of myself. I was like, wow. So you're telling me that every perfectly harmonized in-fed half wave that's resonant has a little bit of, random wire hanging off the back of it.
Electrically, yeah, it does.
Electrically, yeah. I thought
You may
I
not
was
see it, but it's there.
I'm sorry, guys. I was laughing for like a good hour over that.
Well,
My
it's
buddy
like
Mike here saying the counterpoise.
the average person who is not a ham, who's not an antenna guru. They're driving down the highway and they go by and there's the AM stick on the right-hand side and they look at it and they go, oh, look at the antenna. That's only half of the antenna.
Right, the cars.
They're not seeing the whole thing. And what Ziggy just showed is the whole thing. From one end to the other, it is a half wavelength long. It doesn't start at a half wave where you're putting the transformer. It's the counterpoise plus the whole other, what we're calling the half wave.
Yeah, because people.
It's really an off-center fed to an extreme, but it is never truly an end fed. You cannot fit. It's like having a monopole. As far as a magnet, all magnets are dipoles. You can cut it and cut it and cut it. It still has two poles, a north and a south. There's no such thing as one that only has a north or a south.
Well, that's what I ask people all the time. What's the difference between a end-fed half wave with a counterpoise and an off-center fed dipole? And people are like, well, one uses a 49-to-1, and one, there's no difference, right? They're the
Right.
same thing. My buddy Mike is saying the counterpoises are overrated. I think they're misunderstood.
It's okay.
Like
Much like myself.
It's a hard concept.
So here's my fundamental 80, but yet for some reason I'm trying to work FT8 on 10 meters. What do we see here, fellas?
What you're seeing there is higher current, right?
Right here at the
Yep.
yeah. And
So
so,
the
Hollywood
counterpoise
taught me
radiating
it doesn't matter.
the
Don't worry
most.
about. I'm sorry. Go ahead.
Your counterpoise is radiating the most energy right there.
It's real mad. Yeah, you're going to get a lot of CMC on this frequency. But the thing Hollywood taught me is that you always start at the end of your wire and work your waves back.
Yep.
And this is what we're doing. So everything's great all up until we get to our feed point. And now we have high current on both sides. And this has to go somewhere. It's going to go this way.
Right.
It's
So
going
you gotta
to
put a
go
choke.
that way.
Put a choke on that thing.
Choke that thing, do something. But that's terrible. But so this is why it's actually harder and harder and harder. That's why we get the SWR Stairway to Heaven, is because when we start folding more and more, our bands they aren't mathematically perfect.
Right.
They're close.
They're mathematically perfect if the antenna is up in the sky. Really like a mile up.
A mile up.
If it doesn't see the Earth, the Earth is
Free
a conductor.
space.
Yes,
Free space.
the Earth
Here
is
we
a
go.
conductor, and it is detuning the antenna. The higher the frequency you go, the more influence the ground below it has.
Yeah.
So that's why the harmonics don't line up. That's why you have to put a choke or a coil at a certain point, or a capacitor in the middle on the end fed.
So we're at
You're
10
compensating
meters.
for that.
Yeah, a lot of
Right.
people hate on NVEDs because of all these challenges that you get.
It was my first antenna.
Yep.
Well, it was my
Well,
first big boy antenna. But
Yeah.
inverted V was my first antenna.
I love NVEDs though.
Yeah.
I mean, the other thing
Multi-band,
is
one wire.
the far field plots get goofy, and
They work great if you're up in the Zeppelin and it doesn't catch fire. You're in
Right.
good shape. It'll go everywhere. But if you deploy it on the ground, like 99.999% of us do, you're going to see the ground influence that antenna. So it will be easy to resonate it at one frequency, but the harmonics, the further away, the higher the harmonics you go, the harder it is to chase that holy grail of SWR. It's still going to radiate.
What gets tough is that you put up a multi-band antenna like an NFED, and you're using it the same height above ground for every band.
Yep.
Right?
It also does something else that I don't hear a lot of people talk about. The longer the wire, it starts to become a beverage antenna. It changes direction. It's no longer broadside, the signal to the wire. Okay, on the first and second and maybe the third harmonic, it is broadside. After that, it starts changing direction. By the time you get to the 10th harmonic, let's say, it's feeding off of the direction that the wire is going. It's no longer 90 degrees to the wire.
Ziggy's in grid view. He's getting
Oh, sorry guys. I was trying to figure out my far field plot here. Whenever I run it, it's looking like my antenna's on the ground here, right there.
Well, you're looking at an 80 meter antenna on 10 meters. That's the challenge there, right?
No, I'm on 40 meters. I'm on 7.2 at the moment. But I put height, and I even calculated. I put add 10 meters to it, but it's still, when I run my far field, it's on the ground. So I've done something wrong here.
Add 20 to it real quick and see what it looks like.
I mean, it's still on the ground over here in the far field. If I show you again, like this doesn't, you can see it. The antenna's on the ground right here. So I'm trying to fix that.
You have to run the calculate, or what is
Go
it
to
called?
calculate and add some height.
Yeah, see, I got 10 meters here.
But under where it says Ziggy 75 ohm ham, there should be something right there that reruns the calculations.
Right here? No, there's nothing here.
What's to the left?
Yeah, you start it again like that.
Okay, now take a look at it.
Same thing. It thinks it's on the ground. I've done something wrong. It's okay.
It happens.
Yeah, that's not really what I'm interested in. Far fields. What do you want?
Wait a minute. How high did you make it originally off the ground?
Wire edit. Oops, sorry, wrong button. I'm a little clickety today.
Damn Yankees, can you take me higher?
I mean, that's Z1 at 10 meters.
Change that 10 to 20 real quick. Not there. In the calculate tab.
Man, whatever. I'll just move this wire up. I think.
Easy now. Easy.
I got this. There we go.
Easy.
See what I've done. Nope. Oh, it's way up there now. I got to zoom out actually. Yeah, it's way up there. Okay.
Spam's calling me.
Calculate it real quick. Okay.
Yeah, it still thinks it's on the
notice
ground.
how the pattern has completely
3D,
changed.
Hit the 3D far field.
See, I've done something wrong. Anyway, it's fine.
Okay, but look at where the red is. It's in the direction of the wire now.
Oh, the most it's pointed. That's a great thing that you brought up, Hollywood.
Right. That's my point.
Yeah.
Because a lot of people will do this, and they'll make an end-fed antenna for, let's say, 80 meters, and they'll deploy it, and then at some point in their using it, they'll go up to 10 meters. and they'll say, well, it should go east-west because the wire is going north-south. So my signal should go east-west. How come I'm hearing South America real good and I can't hear Germany at all? That's why, because it's now acting as a beverage. It's way too long for that band. It will radiate, but it's not going, the signal is not going where you think it's going to go. It's going off of each end. It becomes a beverage.
It starts folding in the direction that it's going.
If you don't know, look at Harold Beveridge. Google him. He's an RF engineer from RCA way back in the day.
I thought it was because he
Long
liked
Island.
drinking.
Right. The guy was a genius. He was as genius as Armstrong.
Anyway.
But so that's a lot of people say that the radiation patterns on the NFEDs are unpredictable and they get all twisted up about it.
Yep.
And it's there. I guess you could call them unpredictable. I mean, you can figure them out, right? And you can model it. They're just not consistent across the bands, but that's for obvious reasons that you just explained.
They will always radiate. You need to understand, where is it radiating to? What can you expect from it? You will make contacts all day long. But if you're trying for a specific point and you're working the 10th harmonic, might be to your advantage. If it's in the wrong direction, swing the antenna around, because you actually have a very highly directional antenna at that point.
Right.
There are a lot of DX guys that listen to AM broadcast stations off of the beach, and they're using long wires on the ground. They're not, I mean, they're only, 5 feet up, but they're, hundreds of yards long, and they become directional at that point. Even without the resistor at one end, they're bidirectional. If you put a resistor at one end, it's a true beverage. It's directional in one direction. But if you float both ends, then it is not directional in one direction. It's bidirectional.
That's definitely definitely interesting.
Hollywood,
Chuck, what are you working
It's
on
something
there?
to chew on.
What am I working on?
I noticed you keep looking down.
I'm just listening. I started.
You're winding something here. I knew it. Let me get you on the big screen.
Oh man, he's going micro.
What gauge wire is that?
This is 18.
You went with a porky one. I used 20, I believe is what I used.
Ape and I were talking about re-upping.
Well, I have
on
lots
some
of 18 and 16, and I wasn't going to do 16.
Ape and I were working on a project together, and he said, "Oh, I asked him what size wire you got, and he said 18." And I went on the Supply Depot, and I was like, I need 1 click bigger than Ape, so I got 17 gauge enamel wire.
I remember when you did that.
I'm the
Do you
only
want to show this
person
one? I tried this one.
only person on the planet that's using 17 gauge wire for their transformers.
So let me turn the light off. And see
Tell
if
us
it-
all about it, Chuck.
And big in it.
Well, we've done really well with the Poseidon, so I just said, well, let's just. I've got plenty of these around to try, so I wound one, and the problem, I think the band was really bad the day I went out, but it's
It was
really close
non-existent
to a
yesterday.
40. It's really close to a 43 as far as the SWR and all that stuff. So I don't know. I'll
So
try
Hollywood,
another
let me
day.
ask you a question real quick. So
Sure.
he was showing that one. That's the powdered iron core.
Right.
And at a 49-1, there's a lot of windings on that. And so those are lower permeability cores.
Right. Yep.
And I made one and I measured its open inductance on the primary, and it was showing as capacitive, which is something it shouldn't do, right? And it's either
Right.
doing that because it's capacitive coupling of the windings on there because there's so many windings,
Or the VNA is not calibrated right.
or you're getting so much inductance per turn that it's above the core self-resonant frequency, right?
Maybe. I have to think about that.
So I don't think I would use that particular powdered iron, or being candid, any powdered iron for 49-1, but we definitely wanted to check it
The
out.
good news about using powdered iron is it has a much higher temperature that it can withstand before it falls apart.
And it's good for
powdered
lower
iron,
Cigarette
but they get
is go ahead.
The powdered, but they get hot faster though.
I don't know about that. Because it's a more of a pure mix. It's not. It's all of one type. It is a narrow passband. If you look at your tuner on the back of the radio, if you look at the low pass filtering section on any radio, those are not ferrite. They're
Right.
iron because
that's
they have a
because you
very
can-
high Q.
Yeah, I was gonna say because high Q, and you
And
you
they're
can tune
super.
them.
Look at how small they are in a 100-watt radio, and they're taking 100 watts all day long. So
140s.
that
Yeah.
that high Q and that high temperature capability means they're not going to change. They're stable, just like the silver mica cap is a lot more stable.
What about when you operate outside the Q, the resonant part of this circuit though? So that's what like they're not broadbanded like a ferrite, right?
Right.
And so that's where I thought that potentially that they could be holding more energy, and that's where you get that heating comes in.
They're more efficient. They're a lot more efficient. I don't know that they heat up faster. I don't know about that.
I think the heat's going to come with whatever mismatch that you're trying to force
Yep.
into it.
Yeah, the only and it was mismatched, but the only core that I've had melt of one of our nylon frames was powdered iron.
We'll build it on asbestos.
I could peel up some of the floor tiles in the basement.
That's a joke, kids.
Hollywood said, "Buckle up and move on."
Uh-huh.
Okay.
That's great. So, here we go.
But that's why we use PTFE wire, because
Right.
it is going to get hot at some point, or the magnet wire that has no coating other than the varnish, the double coated.
I brought this up for Hollywood because I want to hear Hollywood's explanation as
Oh
to
boy,
everything that's great and everything that's not great about having one of these antennas.
that coax is bothering me.
I figured it would, but it doesn't look like the counterpoise is connected to the shield.
Where's the shield? Right.
Yeah, it's a drawing, fellas. Come
Oh,
on.
okay.
Well, I'm going to be uptight about that. I want
I
to see
know
it
you are.
connected
So we
to
have
the damn shield.
An 8-to-1, 64-to-1. Okay, good.
Okay, so we've got let's see, 8 times 50, right? Is that how we're getting this? Or 64?
Yeah, that's fine. The only thing that's missing is you need to have a choke a quarter of a wavelength down on that coax.
Now, why is that, Hollywood?
Okay, so every time you have a half wave, the impedance repeats. So if it's a let me think about this. If it actually a half, I misspoke. You want it to half wave back. If it's a low impedance point going into the transformer, it's 50 ohms J0 going into the transformer. The common mode on the outside, which there is no velocity factor on the outside of the coax. It's only on the inside where the dielectric is. Okay. So it's just a piece of wire. So it's a 9.99 velocity factor on the outside. If you have low impedance, high current at the transformer, exactly a half of a wavelength towards the radio on the outside of that coax will be another current high point. But a quarter wavelength will be very little current and high voltage. If you put a choke, which is, think of it I'm oversimplifying it, but think of a choke as a resistor in series. A resistor at a high voltage point will have minimal effect, but if you put the resistor where the current is high, it will have a much greater effect. It's a voltage divider. You're adding a resistor in series with a low impedance point. That resistor has a very large effect.
So Hollywood, I always put the choke right at the antenna feed point.
You can do that, but there's probably going to be some leakage that's going to spill over the choke. And it may be advantageous to have some of that coax actually radiate and have some common mode. If you look at the Carolina Windham, which is also an off-center fed dipole,
Right.
okay? The Carolina version wants the coax to radiate, and then you put a choke below a specific point. And so it adds some vertical radiation in addition to the horizontal wire, the horizontal radiation.
Or making like an inverted L.
Filling in
right?
the nulls. Right.
Yeah, because I've seen where certain shortened antennas, right, with like coil loaded antennas and stuff like that, will use the and I'm not talking coil loaded at the base, like somewhere along the radiator. They'll use the coax vertically mounted as part of the radiating element, and then put a choke like 5 meters down or something like that.
Sure. 11-meter days, we used to take a piece of coax and separate, open up the jacket and pull the shield down over itself. It's called a sleeve ballon. When you take the shield and you open it up and you fold it back on the outside, the black part of the coax, and that shield is a quarter wavelength long, and the center wire is also a quarter wavelength long. The distance between them is a half wave vertical dipole. That sleeve ballon stops the current from going and repeating all the way down the coax.
That sounds like a pain in the ass.
No, it's super simple. It's a MacGyver thing. You find some TV coax in the trash bin that's not on fire, and you got to save the day. That's how you do it.
There you
TV
go.
coax. Did you hear that, guys?
You heard it here first.
That was in all the CB books in the 1970s. That was probably the most common antenna to make.
There were CB books?
Oh, yeah.
They used to have CB magazine and stuff like that.
Oh,
I know
73
that.
magazine, CB magazine. They would go to the, what is it? The history of world history of radio, the website. You can spend a year in there and not read it all.
Yeah, that's definitely a good resource for that. And I always tell people people like to hate on the CB crowd, but they have a pretty good rich history of RF engineering back in the day. And then
I started there.
I did too, but I mean I didn't know anything about what I was doing. Still don't. But the other thing is that I've seen some CB guys that are very, very talented with RF.
Yeah. And conversely, I've seen a lot of hams that just want to play music on 40 meters.
Right. Mike saying that he saved all the centerfolds from the old CB magazines. I got to tell you, some of those older magazines do have a little bit of racy stuff in there that would not fly today.
Right.
Like chick in a bikini drinking a malt liquor while operating.
Holding up a CB that's got like 14D batteries in it. It's true. I've got one at work. I dug it out of a box. I was like, that's like $20 in batteries right there.
Yeah, I had a HT CB handheld that took a mess of D batteries, or maybe it was C batteries, but it was like 10 or 12 of them or something. To the point where it was no longer an HT. You know what I mean? Like you couldn't carry it around all day.
And let's not forget the handset in the car that looked like a telephone.
My grandma had one in her Mercedes, and it was a factory option to have Mercedes install a CB into your.
And the CB that was built into the car stereo in the dash. And you had and you had the little converter box. You could use the AM/FM whip on the.
It did. Sure. It used her. Yeah, she had the. Yeah, I remember. I was like, "What is this?" I was like, I learned later. I was like, "Damn, Grandma had a diplexer, right? No, diplexer. What is it? Is that it?"
We got a question for the Professor Emeritus. Doc Brad wants to know about air wound ugly chokes versus the toroid chokes.
Air wound choke has very little inductive reactance by comparison to the other two. You're going to need a lot of it. An ugly choke is going to be a high Q. It will work beautifully at one frequency and one frequency only, but it's not broadbanded. A toroid choke is very broadbanded, depending on what mix you use. If you use ferrite, it's going to be a lot more broadbanded than the iron powder.
Awesome. I was glad you were going to say that, because I'm not a fan of the ugly chokes at all. I know a lot of people love them and swear by them. And
I did one of my 6 meter Matt Yagi.
And
wait a minute,
it's funny.
Are you talking about an air wound choke?
No, an ugly choke is a piece of coax wrapped around itself.
They call it a torus knot.
An air, in a
but
free space.
It's heavy. It's heavy. Coax back in the day when we used those was relatively cheap. Coax is pretty darn expensive now.
$1 something a foot, unless you're
Well, so I call it a Gordian
knot. You need a lot of it. You need a lot of it to make that ugly balance. So
what I learned about ugly balance is if it's common in the 11 meter area, because if you do it right and you actually have testing equipment, you can make a very a very I don't know how to say it. You can make a very band specific
Yes.
choke.
Yes.
You
Or if you're always on
it is
Super Bowl.
it's super tight.
You
Like,
can,
it's-
and you can make it even tighter. You can take a variable capacitor and go wind the thing around a piece of ferrite. Okay. And if you want to make it really high Q, you take a variable capacitor and you tap from the shield on one side of the choke to the shield on the other side of the choke. So you're adding a capacitance in parallel with the inductance of the winding of the coil. And
your
you can
LC circuit
increase
out
that
there.
Q, right? I mean, you can make it normally without the capacitor, you might have let's say 3,000 ohms of inductive reactance. It's very easy to make it 10,000 or more.
That's
Do you need that?
awesome.
No, not
No.
necessarily. But if it's like let's say you have a 2-meter Yagi and you've got common mode somehow coming back, you can dial that thing in and it's completely cut off at the knees. There's no RF coming back now because it's a tuned circuit.
I made a choke for my 11-meter friend, dual bifilar, dual 61 240 cores, and obviously impedance match the wrapping, specifically to the exact point where he was trying to operate. And I was so sweating bullets. I was so close to negative 60 dBm of attenuation. I thought that was
Yep.
bananas.
He was pushing
And-
3 gallons through that thing too, right?
Anyway. Anyway, it ate up some power and it fixed his problem. It was leveling out about 40 to 50 watts of what I call flyback or mismatch.
Yep.
And it was making all his numbers 0, and he was the happiest guy on the planet.
And I'll throw this out too, because it's a voltage divider, the choke I'm talking about.
The dual bifilar?
Whatever type of choke you decide to use.
Yeah.
Okay. A lower Q choke will have more losses. It will not impede the flow of the common mode as well as a high Q choke because it's spreading out that energy over a large frequency spectrum. Okay. So the better the choke works, the more power it can take because
Right.
it's a higher resistance. It's the current that heats the thing up, not the voltage. So if it's a really, really good choke and it's stopping that current, if it's stopping it dead in its tracks, you can have 1,000 watts. You can have 10,000 watts on the other side.
Yeah,
That little choke is going to be super efficient.
it's not going to sweat.
Right.
Mike from Mike's Radio Repair, he's saying that he had Chevrolet factory CBs that had the bow tie badge on the front. That's pretty awesome. I'd love to see those.
I'm so happy whenever he shows up.
Is that like when you got the Texas horns on the front on the and that whole thing is a dipole, really?
Thanks, James. He sent the spec sheet for the capacitor for Mauser. Thank you.
Good.
Oh, that was nice.
Well, we just hit the 1 hour mark. And I think that's what I was targeting for this thing. Did anybody have any closing comments?
Yeah, I do. If you are interested in antennas and traveling waves, I have 3 sites I can post in the chat after the thing is over if you like. But
That'd be great.
Look at MIT has free videos from Dr. Walter Lewin. He's the physics
great.
professor. He's retired now, but look at his video on EM, electromagnetic waves. That's the first one. The second one is Google standing up for standing waves. That's a video on YouTube, standing up for standing waves. And the third one is from the ATT archives. The title is called Similarities of Wave Behavior. You watch all 3 of those, and you're going to automatically be at the top of the list of becoming an RF engineer. Those are the basics, and that's a college course right there. Just watching those 3 videos, and it doesn't have to make your eyeballs turn backwards in their sockets. Hit pause, walk away from it, come back, watch it as much as you want to watch it. But those are so highly recommended. Those 3.
MIT has a few antenna theory videos that are pretty good. They're lectures for like their
They're free for the
graduate course.
taking. Yeah.
Yeah, it's really valuable information. So thank you for sharing that. If you could post them in the comment section, that would be fantastic.
Yep. Done deal.
Thank you, Hollywood, for being here. Definitely
Yeah, thanks.
appreciate it.
Thanks for having me.
Thank you,
All right,
Hollywood,
well-
for coming by. That was great. Great to have you.
And then I'm going to say thanks to everybody in the chat. Much appreciated. And then I'm going to hit the end stream button right about now. But Chuck, did you want to tell them about that other thing?
I can